My name is Andrew Coble, and this is my project for presentation for CE 570. This project, we were tasked with forming the area Jacobian for all the surfaces on my body. My body of choice is a snow cone. As you can see, the area Jacobian is listed right here, followed by my unit normal vectors defined for each surface, the curved outer surface of my hemisphere, and then the bottom surface of my hemisphere. Following that is the scalar field, which is defined as x1 squared plus x2 squared plus x3 squared. Are the last two parts of my snow cone, which are the cylinder and the upright cone. For the cylinder, I only had to define one unit normal vector, which is the outer surface of the cylinder. Finally is the area Jacobian unit normal vector and scalar field for my upright cone. The upright cone's unit normal vector is the curved outer surface of the cone, which you can see kind of got messy right here. These are the plots that MATLAB outputted, where the plot parameterization is listed on the left right here, and the scalar field is depicted on the right as well, which you can also see my scalar field is listed right here, which is x1 squared plus x2 squared plus x3 squared. Now I'd like to discuss my hand-verified area calculations for my three shapes starting with the hemisphere. You can see at the top is the parameterization of the body of the hemisphere, and then listed are the two surfaces right here. You can see the partial derivative is taken with respect to phi and theta because the radius is held constant at 4r and comes out to be r squared sine phi. Then I took the double integral of the function and solved for a surface area of 402.123. Next, I solved for the area Jacobian of the bottom disk, which is just the radius, and then integrated it with respect to r and phi. Since theta is held constant, I got a value of 201.062. Surface area calculation for my cylinder, where the body and the surface is defined at the top. There is only one surface to solve for, which is just the outer surface that surrounds the cylinder. I took the Jacobian with respect to theta and z, which resulted in the radius, and then integrated it with respect to theta and z, since the radius 4r is held constant, and got an area of 100.531. Next is the surface area calculations for my cone, where the body and surface are defined at the top of the slide. There is one surface to solve for, which is just the outer surface of the cone. I took the Jacobian with respect to theta and z, which resulted in a value of RLZ over 81h squared, where L is square root r squared plus 81h squared. The surface area calculation integrates over theta and z, since the radius of the cone is 3r at the base and results in a value of 357.645. I will verify my MATLAB calculations with my hand calculations. As shown in the snapshot above, the surface area and the volume calculated by MATLAB is identical to the values that I calculated by hand. The flux verification will be shown later. Now I will go over my unit normal vector and flux calculations. Starting with the hemisphere, my unit normal vectors in MATLAB are displayed at the top, and the hand derivation of those can be seen below it, where I multiply 1 over the area of the Jacobian by the partial derivatives cross product with each other. Then I solve for the flux, which is represented by the body as a function of the scalar field multiplied by the area Jacobian and unit normal vector. I then did the same for the bottom of the surface of my hemisphere and for the single outer surface of my cylinder. Repeated the same process for my upright cone, where I listed my unit normal vector for my MATLAB code, and then my hand calculations for my unit normal vector, and then my hand calculations for my flux. Seen here is the MATLAB listed total flux value, and then also my hand calculated total flux value, which I end up having to plug all my equations into MATLAB, which resulted in a value of negative 7.62 e to the negative 11, negative 2.13 e to the negative 11, and 6,433.98, which basically just rounded off to 0, 0, and 6,434, which is verified with the MATLAB value. Thank you for watching and have a great day.